I'm Will Kirby. I'm a grad student of Peter Love at Tufts University in Boston, USA. And this is also joint work with Andrew Tranter, who was Peter's postdoc when we were doing this. And he's now working at Cambridge Quantum Computing. Contextual subspace VQE, and we'll get to that in the last section. And I'll be giving an overview of results from 3 papers here, but the emphasis will be on this third and most recent one. So in this first part, I will discuss contextuality and how it can appear in Hamiltonians that we use variational quantum eigensolvers, or VQEs, to study, and I'll also review what VQE is. Then I'll talk about what it means for a VQE instance when the corresponding Hamiltonian is non-contextual, which, as we know, we should expect to mean classical in some sense. And finally, I'll talk about what leverage we can gain from these considerations when the Hamiltonian is contextual, which is true in the general case. And this will lead to this new hybrid quantum classical approximation method that I mentioned for general Hamiltonians, where we partition the Hamiltonian into a non-contextual part that we simulate classically, and a contextual part that we simulate using a VQE algorithm that requires fewer measurements and qubits than it would for the original Hamiltonian. And I am going to focus on presenting main results without going into proofs. For those, I'll refer you to the papers. Okay, so let's first quickly review how VQE works. VQE, again, is variational quantum eigensolver. The goal is to find the ground state energy of some Hamiltonian H. First, we decompose this Hamiltonian into a linear combination of Pauli operators P in some set S with some coefficients H sub P. And this can always be done for a Hermitian operator, but we assume that this can be done classically efficiently for the purpose of this algorithm. And this is the case for many physical Hamiltonians of interest, for example, using known fermion to qubit mappings to take a second quantized fermionic Hamiltonian to a Hamiltonian that acts on qubits with Pauli terms. Then the quantum algorithm, for the quantum algorithm on the quantum processor, we prepare ansatz states and then separately estimate the expectation value of each Pauli term by repeatedly preparing ansatz states and measuring until we assemble enough statistics. Then we just classically combine these according to the Hamiltonian formula to find the expectation value of the full Hamiltonian. And then we take that whole thing and use it as the objective function in a classical optimization procedure. So here's my objective function for the expectation value of the Hamiltonian, and here it is expressed as the expectation values of the terms. So we use this as the objective function for a classical optimization procedure that varies the ansatz parameters, which I'm denoting theta here. So we're attempting to minimize this function to find the lowest expected energy, which, if we're searching the whole space, is the ground state energy. So we wanted to identify what separates this algorithm from a classical algorithm. And the approach we took is to focus on the set of measurements that are performed. And I should note that the other part of the quantum step in the procedure is these ansatz preparations. So one could also consider how quantumness can appear there, but the problem itself is defined by the Hamiltonian and by the measurements performed. So that's what we just focus on for this work. And I'll discuss this distinction a bit more later. But for now, it's enough to say that we want a means for identifying intrinsic quantumness in the set of Pauli terms in the Hamiltonian. And we already know that because of the name of the workshop that this is going to mean contextuality. So to get into thinking about contextuality of sets of measurements, suppose we want to construct what is essentially a realistic hidden variable model for S. S, again, is just the set of Pauli terms that appear in the Hamiltonian, which is also the set of measurements that are being performed on the quantum computer repeatedly, over the course of this algorithm. Well, this hidden variable model should consist of 2 pieces. The first piece is some set of joint value assignments to the Pauli operators in S. And this just means that we're assigning values plus minus 1 to each of them because those are the eigenvalues. And we can think of these joint value assignments as something like phase space points for this classical model. And in our realistic interpretation of the model, they would represent our state of knowledge of I'm sorry. In our realistic interpretation of the model, these correspond to the classical real values. I got ahead of myself there. Then the second piece of the model is some set of allowed probability distributions over the joint value assignments. And these are what, in the realistic interpretation of the model, represent the state of knowledge of the observer of the joint value assignments. So these probability distributions, sometimes also called epistemic states, because we're interpreting them as about knowledge of the observer rather than something about physical reality. And in our model, they're taking the place of quantum states. So these replace quantum states. And implicitly included in the set of allowed probability distributions is some uncertainty relation that restricts how much joint knowledge we can have of the observables in the case that some of them might anti-commute or not commute. So such a classical phase space model with an uncertainty relation is sometimes called a quasi-quantized model, which is a term that was coined by Robert Speckens. But as we all know well by now, in general, there are obstacles to constructing such models for quantum mechanical systems. And the particular obstacle that we're going to focus on has been called strong contextuality in various prior papers. I think it's also gone by other names. But what we're asking here is whether it's even possible to set up the joint value assignments to our set S. Are we going to run into contradictions when we do this or not, depending on what Paulis are included in the set S? And I am just going to refer to this as contextuality for simplicity in the rest of the talk, but keep in mind that I'm talking about strong contextuality of measurements. So to show that a set of Pauli operators is contextual, we will rely on inferences that we can make about their values if we were to try to construct classical values for them, as in a model like the one on the previous slide. So suppose we have some assignment of values to our set S, and suppose P and Q are some pair of commuting operators in S. So they commute. Well, our model has to reproduce the predictions of quantum mechanics for the observables that it describes. So an observer could, if they chose to, measure P and Q simultaneously, obtaining the values that are assigned by the model. And from these, the observer could infer the value that they would have to obtain if they measured the product, PQ. This product is itself a Pauli operator up to a sign, which is always true for products of commuting Paulis. So for example, if we had just Pauli X, this is like sigma X, acting on each of a pair of qubits, I'm suppressing tensor product signs. So this is like sigma X tensor identity and identity tensor sigma X. If we have them acting on each of a pair of qubits, then from any value assignment of plus or minus ones to these two, we can infer the assignment to their product XX. And we can show, visualize such an inference with this little tree here. So this brings us to a more technical definition of contextuality. The set S of Paulis is contextual. Again, this is strong contextuality. If any joint value assignment to S necessarily violates some inference relation of this kind. And I do just want to emphasize here that we're going to allow inferences of the values of operators that are outside S, as long as our initial set that we're inferring from is inside S, the set of terms. I think this is a slightly unusual choice. Oftentimes people are only interested in inferences within some restricted set. But practically, this is because we'll later want to be able to freely use inferences to manipulate the hidden variable models that we're constructing. And slightly more abstractly, we can think of this as meaning something like, even though we're looking at this subtheory of quantum mechanics that's characterized by the measurements in S, we want it to still exist within the broader framework of quantum mechanics. So our model doesn't rule out measurements, it just might not describe all of them. And this will be important because later we're going to be constructing this hybrid algorithm where the non-contextual part is described by the hidden variable model, but there's also a contextual remaining part that runs on the quantum computer. So if our hidden variable model predicts the value of some observable that isn't in our initial set, we still need to keep track of that. And also I'll note that this is just the same as insisting that we look at contextuality of the closure under inference of S, which is a criterion that at least Robert Rausendorf's group has used in their work on phase space models for quantum computing. So let's see an example quickly of how this type of strong contextuality can appear. Suppose S consists of Pauli X acting on each of a pair of qubits, and now also Pauli Z acting on each of a pair of qubits. Well, if we have some value assignment to S, we can infer the values of the additional operators that are shown in these trees, where each of these little 3 vertex subtrees is a single inference like we talked about before. So the child nodes commute and the parent node is the product of the children. And in particular, from these 2 trees, we can infer that the values assigned to both plus YY over here and minus YY over here have to be the products of the values in the original set. But this is a problem because it means that these values, which have to be plus or minus 1, assigned to plus YY and minus YY have to be the same. So this is a contradiction. And this means that any assignment of values to these trees must violate at least one of the inference relations that are encoded in these trees. And this implies that the set S is contextual. And you've probably already noticed, because I wrote it here on the slide, that this example is just a recasting of the Perez-Morman square, but we're just starting with a subset of the square and we're inferring the rest of the square from it, because again, we're allowing these inferences to go outside of our initial set. So this brings us to a first main result, which is a necessary and sufficient condition for contextuality of an arbitrary set of Pauli operators. And actually, we're going to focus on the non-contextual case for the next few slides. So I won't prove this here, but the set S of Pauli operators is non-contextual if and only if it has this form. So what's going on here? Well, first of all, there's allowed to be this subset script Z of S, such that every operator in Z commutes with every other operator in S. So if S were a group, this would be like the center. And then in the remainder of S, which we call T, this script T, commutation is an equivalence relation, if and only if S is non-contextual. So as we heard shortly ago, commutation isn't an equivalence relation in general, but if it is on this particular subset, then we have non-contextuality. And we can let these C sub i's denote the equivalence classes of commutation within T. So Pauli's in the same C sub I commute and Pauli's in different C sub i's anti-commute. So the non-contextual sets of Pauli operators are exactly those with this form. And since S defines the set of measurements performed on the quantum computer in a VQE algorithm, we say that the VQE instance and the associated Hamiltonian are non-contextual if and only if S is non-contextual. So we apply the same criterion. Okay, so given this definition of non-contextuality and given an arbitrary non-contextual Hamiltonian, we want to actually construct our classical hidden variable model for it. So first, we can efficiently classically construct a reduced non-contextual set from which we can recover the original set of terms by inference. And that set is shown here. The key feature of this set is that it's independent, which means that no value of any operator here can be inferred from the values of other operators in the set. And this means that all joint value assignments to the set are allowed, as opposed to just some, which is the case in general for a non-contextual set. So since we recover joint value assignments to the original set by inference on this, this is just a simple way to enumerate all of the allowed joint value assignments for the original set. So what is in this set? The components are first this subset G, which is an independent generating set for the fully commuting part, script Z from the previous slide. And then these A sub i's, which are just one element from each of the commutation equivalence classes C sub I from the previous slide. So we're just taking one element from each of them. And actually, G technically needs to be an independent generating set for the maximal set of Pauli operators that commute with all of the terms in, or a maximal set of Pauli operators that commute with each other and all of the terms in S. But we can still efficiently compute that generating set. So everything is efficiently classically determinable here. And the coefficients, sorry, I got ahead of myself. So every term, what this implies is every term of the non-contextual Hamiltonian is some commuting product of these generators So writing the Hamiltonian in that form gives us this expression. So the B's are arbitrary products of elements in G. So this is just the closure of G. And the coefficients are the same coefficients in the original Hamiltonian, just under some labeling that we can also efficiently classically calculate. So at this point, we've fully described the joint value assignments in our classical model. All that remains for us is to describe the allowed probability distributions that correspond to quantum states. And here we have a bit of room for judgment. One approach would be to figure out exactly what probability distribution corresponds to each quantum state and let those be our set. And we can prove that there is indeed a probability distribution corresponding to each quantum state, but parameterizing these looks hard. So instead, we can use this more restricted set with an eye towards what we want to use it for, which is just generating expectation values of the Hamiltonian. And for that purpose, it's enough to allow this set of joint expectation values. And we would recover the joint probability distributions from these just as product distributions of the marginals that correspond to these expectation values. So what's happening here is we're assigning definite eigenvalues plus minus 1 to each of the commuting generators, G sub j, these are just the elements of G, and asserting that the expectation values of these anti-commuting generators, A sub I, lie on a unit sphere of the appropriate dimension. This R is just a unit vector, a real unit vector. And we can prove that these joint expectation values are sufficient to recover every expectation value of the non-contextual Hamiltonian. To give a sketchy idea of why this is true, the G sub j's all commute with the whole Hamiltonian. So there's a common eigenbasis for them as well as the Hamiltonian. And then the A sub i's all anti-commute, so we get a sort of higher dimensional block sphere for their expectation values. Okay, so now we can insert these parameterized expectation values, parameters qj in this vector R, into the Hamiltonian to obtain a parameterization of the Hamiltonian expectation value. And this works only because the expectation values for the commuting generators are plus minus 1. Normally, the expectation value of a product is not equal to the product of the expectation values, but in this special case, it is. And there turn out to be at most 2n plus 1 of these parameters for an n-qubit Hamiltonian. So this expression that we end up with is a classical objective function of order n real parameters that can reproduce all expectation values of this non-contextual Hamiltonian. Yeah, but only in the non-contextual case does this work. So one immediate consequence of this is that this provides a, in quotes, dequantization of non-contextual VQE, where we replace the quantum part of the procedure just with this classical objective function. And I put dequantization in quotes because this doesn't prove that there can't still be a quantum advantage for non-contextual VQE, because there could be some clever way to use ansatz preparation to get an advantage. But the possibility for quantum advantage is restricted to this, much like in the quantum approximate optimization algorithm, or QAOA. And the second conclusion, which is related, is that the non-contextual Hamiltonian problem is in NP. And if you're interested in that, you can ask me about it after. Okay, so now we've been talking for a while about when a Hamiltonian is non-contextual and what we can do in that case. But what if we're given a Hamiltonian for VQE that's contextual? Well, we know that that means that we can't build our classical model for the full Hamiltonian. But we could try partitioning the Hamiltonian into a non-contextual part, this H sub nc, and whatever terms are left over, which will in general be contextual if our Hamiltonian is sufficiently complicated. And we can choose the non-contextual part to be as large as possible using some norm of our choice and maybe some heuristic. And again, ask me about that later if you're interested in how to choose this. And then we can use our classical method to approximate the ground state energy of the non-contextual part, just the H sub nc. And we could just take that as an approximation to the ground state energy of the full Hamiltonian, given that hopefully the non-contextual part covers a lot of the Hamiltonian. And we tested that for some example Hamiltonians, and it works okay. But generally, it's not accurate enough to be useful, which for the sake of quantum computing, we should be relieved about, because if we could do too well with our classical model, then there's not so much point in running things on a quantum computer. But luckily for us, it doesn't work too well in general. And I'll show these results in a couple of slides. But for now, let's consider how we may do better. Well, the energy minimizing parameter setting for the non-contextual part, which we can call the non-contextual ground state, it's just this parameter setting here, This corresponds to some subspace of quantum states. And in fact, this subspace is very similar to a stabilizer subspace. Since the parameters Qj are plus minus 1 in their eigenvalues for the commuting generators, the non-contextual ground state lives in the corresponding common eigenspace of the G sub j's. And it also turns out to be in the plus 1 eigenspace of this operator script A. Script A is a linear combination of the anti-commuting generators A sub I, weighted by their expectation values R sub I in the non-contextual ground state. And since R is a unit vector, any normalized real linear combination of anti-commuting Pauli operators turns out to be unitarily equivalent to a single Pauli operator. So script A also has eigenvalues plus minus 1, and we're interested in the plus 1 eigenspace of it. So we can think of the non-contextual ground state as a stabilizer subspace in which one stabilizing Pauli operator has been rotated by some unitary that preserves the other stabilizers. So it becomes this script A. So what can we do with this? Well, understanding this subspace means that we can obtain a contextual correction to the non-contextual approximation of the ground state energy by minimizing the energy of the contextual part of the Hamiltonian within the subspace that corresponds to the non-contextual ground state. And we would do this using an actual quantum VQE algorithm whose ansatz is just restricted to that subspace. That idea is summarized on this slide. We assemble the expectation value for the full Hamiltonian out of the non-contextual contribution that's estimated classically and the contextual correction that's estimated on the quantum processor. And when we restrict the contextual part of the Hamiltonian to the subspace corresponding to the non-contextual ground state, it becomes simpler. So again, this is the part that we're looking at on the quantum computer. But each non-contextual generator, the G sub j's and the script A, removes 1 qubit's worth of freedom in the non-contextual ground state. So the contextual correction Hamiltonian ends up being a Hamiltonian on a number of qubits that's given by the original number of qubits n minus the number of generators, which is the size of G plus 1 for script A. And I'm running a little bit low on time, so let me see. Yeah, so on the next slide, I'll show you the results of applying this. For now, we have this classical computation plus a small VQE algorithm that combine to approximate the full ground state energy. But what if we have more qubits than we need for this small VQE, but still not enough to do full VQE on the full Hamiltonian? Is there some way we can use these extra quantum resources? And the answer, as you can see, yes. One thing we can try is to just stop restricting to the eigenspace of some of the non-contextual generators. So for each that we stop restricting to, we regain 1 qubit's freedom in the quantum search space. And in particular, this lets us use exactly all of the available qubits on whatever quantum computer we have access to. So maybe by doing this, we can get a better overall approximation. And I'll note that the search space still includes the original search space, so we're guaranteed to do at least as well. And we refer to this whole collection of ideas as contextual subspace VQE or CS VQE, because the quantum search space is the contextual subspace that encodes the degrees of freedom that are left over after we fix the non-contextual part. So finally, let me show you some pictures at long last. We get to test how well this method works. So these graphs show how CS VQE performs on a collection of molecular electronic structure Hamiltonians. And I should note that we simulated the quantum parts of the algorithm classically still, which is tractable for these system sizes. So each curve corresponds to a particular molecular atom. The x-axis is the number of qubits used on the quantum computer, and the y-axis is the overall error in the ground state energy approximation. So the leftmost point in each curve, it's 0 qubits. These are the pure non-contextual approximations. And as we go to the right, we use more and more qubits on the quantum computer until at the rightmost point in the curve, we're simulating the full Hamiltonian using regular VQE. So no classical part left. We're just doing the full Hamiltonian on the quantum computer. And the black lines here mark chemical accuracy, which is just a rough cutoff for the accuracy you need to do reasonable MD calculations, roughly speaking. So the nice things that we see are, as expected, using more qubits gives us lower errors. And in most cases, we reach chemical accuracy before we're using all of the qubits for the full Hamiltonian, in some cases quite dramatically, as in some of these big Hamiltonians. So the hope is that we can use this method to simulate larger molecules on smaller quantum computers while still getting results that are accurate enough to be useful. So with that, here are some references, and I'd like to point out in particular that our code is on GitHub now at this link. So please try it out. Feel free to contact me if you have issues, suggestions, or requests. And a big thanks to the organizers for asking me, and thank you all for your attention.
Thank you. We have a few minutes time for questions.
Can I ask?
Yeah.
Yeah. Hi, Will.
Hi.
So you talked about this non-contextual Hamiltonian problem to be lying in NP. So do you have any idea of which particular set of polys are making that classical hardness? I mean, is it these weakly contextual polys? Is it possible?
So where I'm just trying to find where I went past. Here it is. So you're asking about the classical hardness?
Yeah, I'm asking which specific set of polys do you think are making this classical simulation hard? Is it possible that those are weakly contextual polys? Since you are only talking about strong contextuality, is it possible that maybe those set of polys
I see. I don't think even I think you can get classical hardness without any contextuality at all. Like, for example, you can encode satisfiability problems like 3-sat in a diagonal Hamiltonian that's only made out of Z-Pauli operators. So and that's NP complete. So finding the ground state energy of that will be hard for sure, and that's like a fully classical thing. On the other hand, if you do have contextuality, that if you added contextuality, that can only make things worse, or it can't make things better for you classically. Right. So
yeah,
does that answer your question?
Yeah, I mean, have you identified any specific set of polys that is leading to this classical hardness, or I mean, you just generically show that this problem is NP complete actually, right? But
yeah. So I mean, even if you just like I said, if you take if you choose some suitable random set of diagonal Pauli operators that are at least 3 local and give them random coefficients, that should be hard to find the ground state energy. In the worst case, of course, like it's NP complete.
Yeah. Okay.
Yeah.
Thanks.
And yeah, so if you that's sort of the case where the Hamiltonian completely commutes, so it's an even weaker, it's an even stricter condition.
Yeah.
Yeah.
Thanks.